Hello people, welcome to a new tutorial where I will teach you how to design gas targets for wake-field accelerators and not only. In this tutorial I will teach you how to design a symmetric slit type nozzle, or what I call a chimney nozzle. You will see in a short time why I call it chimney. In this tutorial we will use a three-dimensional case with multi-zone mesh, and this type of nozzle will generate very low gas density profiles, and also very long. These nozzles can have a length from a few millimeters up to meters, but we will see that meters long, although is theoretically possible, is not feasible because not only the length is very long, but also the height is very high. So that's why it's not feasible. So let's get started. As usual, drag and drop from analysis systems the workflow for fluid flow with Ansys Fluent. Let's give it a name. So chimney nozzle 3D case. Of course it can be only 3D, since we don't have any rotational symmetry. We cannot use 2D axisymmetric, and 2D is not suitable for this kind of simulation. Right click on geometry, and you can draw the nozzle using space claim if you want. I prefer design modeler. Choose whatever you want. Also, you can draw the nozzle using any CAD program and import it here. It's up to you. Whatever you choose is okay. Click on this, on design modeler. The program starts. All right, and now units, I will use millimeter because the nozzle is big but not that big, so it will be a few centimeters big, so it's suitable. The smallest parts are millimeter size, so that's why I choose millimeters. It's easier to see the nozzle, or to see the drawing. Okay, let's start. So first we will draw the inlet. So the inlet is rectangular. So we go create primitives, box, and as always the flow is in X and Y direction. So I will choose in X direction 10 millimeters or 1 centimeter long, and X and Y it will be 2 and 2 millimeters. So something like this. Generate. Alrighty. And next one, create a new plane. And here the Y plane. So you see, we will need a plane where we will draw the exit of the nozzle, which will be a rectangular shape. So as you can see, if we orient this one, so it has to be the rectangular shape, that will be the outlet, has to be in this direction, so it will be Y, ZY direction, or ZY plane, more correctly said. And we will choose XY plane. Before we are doing this, I forgot to do something. So the box, so as you can see here, is in the plane, the coordinates are in one corner. It's not a good idea to have it like this, because makes the rest of the drawing difficult to make. So we will put it exactly in the middle, and for that all we have to do is just translate the box. So -1 and -1, again generate, and you see now it's exactly in the middle. Use scroll to zoom in and zoom out if you don't know this. Okay, so let's go back, let's create the plane. So we will have as a base plane XZ plane, and we will translate it to a certain distance where we want to have the outlet. And for this chimney nozzle, how I call it, the trick is to put the inlet as far away as possible from to put the outlet as far away as possible from the inlet, and only in that case you can generate those nice flat top profiles. So keep in mind always the outlet as much as possible. Of course, don't put it ridiculously far away. You have to go it in steps. You know, put it first close and check after you run the simulation, check the density profile. If it's not as you want, it's not flat enough, or if the shape is not as you want, then you move it farther and farther away. So until you reach a point where you are satisfied with the results. Alrighty, so we choose here YZ plane, so you can click here or you can click here, so you can choose the plane here, new plane, click on it. All right, and now let's transform. So first transformation that actually the only transformation that we will do, we'll just offset Z. So don't worry about this one. If you can always go back to make changes if you chose the wrong settings. So let's say I want to move it 10 millimeters. You see now that will tell you, it will show you where it will move if you actually choose this number or this distance. And see it. Now we don't really want there. In the first instance, let's put it at 20 millimeters. We will move it later more, but just to see what we are doing here. All right, and generate. Okay. And now we have here the new plane, and in this plane we will draw a rectangular rectangle. So it will be something like here. So click on this one, look at, zoom in. So this is what we have. And if you put it so close, I mean the plane in the first instance, it will help you a lot to have a reference where to draw the outlet. So that's why I put it like that. Rectangle, rectangle. Sorry, my pronunciation is not the best. Okay. And draw rectangle, so like this. And now let's define the dimensions. So we want the rectangle, so in this direction it will be as big as the inlet, so 2 millimeters from here, and from here let's say we will put maybe 2 centimeters or something like this, or 20 millimeters. All right, so horizontal, click, click. All right, and click here, click on axis, and vertical, like this and like this. And now let's define them. So on vertical we want 1 and 1 the other side, and here we want so we want 1 centimeter in one side and 1 centimeter the other side, so 10 and 10. Right, great, generate. And now let's go back. If you move the geometry, we see what we have here. So we draw the outlet, and now we need to draw the wall or the geometry from here to here. It's very easy to do it. So just create and go to skin loft and profiles. I hope it's this one, and from plane 4 this one. Okay. I think I made a mistake here, so it's not skin. So I think it's thin surface. Is it? Okay. Yeah, I think it's thin surface. I haven't done this simulation in a while, so it's possible that okay. No, it's not this one. So it's this one and sketch. Let's see. So if you choose in the wrong way, you will have here a warning. So in this case, so this surface and this sketch. So concept. Okay, yeah, so that was my mistake. So you have to choose the sketch first, and after that the face, add material and generate. Yeah, so that's why you have to practice quite regularly, because you can forget things. All right, so now, from my experience, if you are trying to to run a simulation with the outlet so close to the inlet, you'll see that the profile is most probably Gaussian type. So the highest density will be in the middle, and it will be Gaussian shape. So that is most of the time unsuitable for Wakefield accelerator experiments. So let's increase the distance. So this is 2 centimeter. Let's put the plane. So this is 2 centimeter. Let's put it at 20 centimeter, something like this. Click generate, and now if you zoom out, this is the actual nozzle. Now you can see why it's called chimney, because it looks like a chimney. All right, so this is the nozzle. Now let's draw the outlet. So not actually the outlet, but a region outside this slit part. So this is the actual outlet of the nozzle. But we will draw a region outside, which will call it pressure outlet, and that has a vacuum pressure of a few millibar or even less. So let's draw it, and for that one we will, so keep in mind this part is 20 centimeters from here, here is the inlet. So create primitive box, and now the box is we will have to give it dimensions. So in X, let's say it's 5 millimeters. Let's not make it too big because it requires a lot of mesh. And Y component, let's make it so the slit is 2 millimeters. In total, let's make it 6. No, so Y is in this direction, so it has to be bigger than the slit type, the slit part, or the outlet part. So if it's 20 millimeters, let's make it 30 millimeters. And Z component, let's make it so if it's 2, let's make it 4. And again, now let's put it exactly in the middle. So that's why initially we put the coordinates exactly in the middle of the drawing. It's easier after that to draw the rest of the geometry. So here on Y, let's move it -15. So you see now how it moved. And here again -2 to move it like this. And we have to do something else. Now we need to translate this from here to here. So here we will put 200. Generate. So here is our outlet. You see it like this. So this is pretty much the entire nozzle. Now it's keep in mind that it's very important to have this section about 1 centimeter. If you make it too short, the flow will be destabilized very fast, and even if this part is very long, it's possible that the density profile will be distorted. Also, if this when you run the simulation, if this part is too short, the flow expands too fast from here in this region, and the numerical method doesn't like it, and it will start diverging. So it's better to have this one to control the simulation and also to control the density profile. Alright, so this is pretty much everything. We don't have to do anything else here. We close it and save it, Control S. Let's start the mesh, or the meshing program. All right, this is the mesh. Now let's start with defining the boundary conditions. So click on this one to rotate the nozzle. Click on face, this one, right click, create name selection, and let's call it pressure inlet. Okay, the wall, we don't have to define it. Let's define just the outlet, or this region that is vacuum. So again, if you keep control pressed and with left click this, and let's select the regions, release control, press on rotation, and so that we can choose the rest of the surfaces. Click on face, press control on keyboard, and we have all the surfaces. So pressure outlet, okay. It's always good to check. So pressure inlet, you see it points where you have the pressure inlet. Check this to avoid in case you forgot to select some surface, and here we have 6 faces. Again, it points where you have the pressure outlet. You can define the wall or not, it doesn't really matter. When you import it in Ansys Fluent, it will detect automatically as a wall. Now the mesh, as always, if it's possible, introduce face meshing and introduce method, and here the geometry and method multi-zone. If it's not possible, then the only option that you have is without face meshing, so you need to take it out. Just choose Cartesian, so this one. Sometimes it's not possible. In this case, I think it's possible. And face meshing, we choose, so just click on any surface, Control A to select all the surfaces. If you know what you are doing, you can also mesh only a certain surface. It helps the meshing process. So as you gain experience, you will see how it's better to what options are they work or not. And mesh. Now element size, by default, let's keep it as it is. It's quite big. It's quite big cell size, but just to see what it's doing, update, right click and update, and boom, this is it. Everything is okay. Now here we have to do at quality the smoothing. It should be high, and mesh metric, we want to see statistics about the quality of the mesh, and here it is. This should be as close as possible to 1 in this case, and here always check to have only hex mesh. We shouldn't have TET or pyramidal cells and so on, so only hex. And statistics, you can see here how many nodes and elements we have. This is very, very big mesh or very big cells, so it's not suitable. Let's click here and reduce the cell size, so 0.005. Let's see how many we have. Remember, if you are using Ansys Student, you are limited to 1 million cells. So even if you put here a very, very small element size, you will not be able to run the simulation because you are limited. Otherwise, it doesn't really matter. It will work, but keep in mind, you know, more cells you have, the longer the simulation it is. But if you have, if it's required, you know, to see shocks and small features of the flow, you will need to have a very small cell size. So right click, again update, and let's see what it's doing. Yeah, it's a bit better. So we have about 200,000 elements, and again everything seems to be fine. Let's reduce it a bit more. Yeah, for this kind of geometry, this is quite big mesh, quite big geometry, so you will need maybe 2-3 million cells to have an accurate result. But I will not be really stressed now to do that. I just want to show you how to do it, and feel free to change all of this as you want. Okay, so right, let's put here a 2. Let's see how many cells we have. Now it takes a bit longer because we'll have many more cells. So if you click here, left click, you can see the meshing, how it's going, so you can see the status. Because I mean, there are multiple steps. It's not only it just fits simple cells, and needs to make sure the quality is proper, and all the elements are properly are properly chosen. Okay, so here we have 3 million and something cells. I will keep it as it is, but you, depending on what you are doing, remember, not more than 1 million cells for an Ansys student. Right, so we have all of this. Let's say I'm happy with the number of elements, I'm happy with the quality, and so on. So I just close. Okay, if everything is fine, you have here check mark, but the Ansys Fluent or the Ansys Workbench has a bug. Sometimes the mesh seems to be alright, so you have here the check mark, but when you're trying to import in Ansys Fluent will throw an error and it will crash. Don't worry, that means you have to go back to mesh and see if the mesh is alright, so you change the meshing. So most probably you have to change from multi-zone to Cartesian mesh. Okay, let's start Fluent. And now double precision, always double precision when we want an accurate result. Here you can choose to display mesh or not. If it's a huge mesh, so I'm talking about many millions or tens of millions, it's not a good idea to display mesh because it takes a lot of time and it's not really important to see the mesh in Ansys Fluent. Here for processes you can choose for Ansys Student. I can choose many more since I have license, Ansys license. Okay, start. And now the mesh is imported in Ansys Fluent. We wait. All right. The outlet, you see the arrows pointing out. That means there you have the outlet, and arrows pointing in. That means you have the inlet, and automatically the rest of the boundaries are defined as walls. Scale, if you draw in millimeters, put millimeters here. It's the rest of the it's easier to, when you plot stuff, to have it in millimeters. You'll see it properly. Okay, so it's good to see here the domain, so -15 to 15, so that will help you when you will plot stuff. So always write down these values. So for instance, I write down -15 right here on my paper, -15 to 15, and the outlet is a 200 millimeters above the inlet and extends up to 205, and the other is to 2. All right, close. You don't have to do anything here. Anything else, check. This will check the mesh. If you have any problems with the mesh, here you will have a warning. This also will help you to see the minimum volume. Will tell you, so depending on what features of the flow you want to see, you realize that the mesh is too big or maybe too small. But of course you can do this in the meshing program as well. But here just do the final check before preparing the simulation. Report quality. If you know the definition of these ones, then you'll see, you realize if it's a good quality or bad quality mesh. And units, here I don't like to use kilograms per cubic meter, but I use, so here I have a factor which I calculate using transforming pressure to density, and this factor is valid only for helium. So 10 to, I already calculated, so I know it. So if you use helium, you can use this factor, and it's about 0.0064 something. It doesn't really matter right now. Okay, and this is, you can define any units, but keep in mind when you export the data, it will export in international units. So even if you define it here, the units in atoms per cubic centimeter, it will export in kilograms per cubic meter. And also the units for the length, it will not be in millimeters, but it will be in meters. So you have to convert everything after you export the file or the result file. Okay, density based, and we will use steady case, not transient, because it's faster if you are using steady. Transient takes a much longer time and takes much more computing power. Probably in the future I will show you an example. Right now we will use just steady. Is enough to get the density profile required in our experiments, or more specifically in the plasma based wake field accelerators. Models, we choose, so double click on energy, we use the energy equation. Always viscous by default is taken k omega. This is for supersonic flows with walls corrections. So it will with wall corrections. If you want to see more, what does it mean? So if you open this one, press help, and it will open the documentation. So if you have local documentation, it will open local documentation. Otherwise it will open on browser, and you will see there this window, and with explaining each option that you have here, and it will give you the formulas and the theory and the best choice depending on what case you are running and so on. So press help if you need to know more about this. I will not do that, just for brevity. Okay, models, materials. At materials we need to import helium gas. So we need the details about the helium, because this is what we will use in our simulation. And in most of wake field accelerators, we use hydrogen or helium, sometimes doped with nitrogen, neon, or other inert gases. But definitely the main gas will be helium or hydrogen. So that's why I use this one. Copy, close, and here after we choose helium from this option, and now we have to use as an ideal gas. So so even if you choose the ideal gas, the rest of the properties of the gas are the real ones. You can run the simulation as a real gas with all sorts of approximations, but from my experience I haven't seen any difference between the results run with this option, ideal gas, or a real gas. In other cases it might make a huge difference, but not in this case. Change, create, close. All right, and here you have besides fluid, you have an option solid. So this defines the walls. In our case, the walls are ignored, so they are infinitely thin, adiabatic, which means there is no heat transfer between the gas and the walls. If you take into consideration the walls, then you have to define the material, which is usually a metal, and in that case you need the properties of the wall. We will ignore it here. Now double click on cell zone conditions, operating conditions. So this is if your reference. So if the nozzle is surrounded by air, it will be atmospheric pressure here, but it's surrounded by vacuum, so we need to use 0. And now expand, so cell zone conditions, double click on fluid, and by default takes air as gas. We need to click on this one and choose helium. Don't forget this one, otherwise you will have air in your simulation. Now it's good to check at this point if helium is defined properly, or properly means as ideal gas. Click on that one, and if this one is correct, just close, apply, close. That's it. Now let's define the inlet. So the inlet, let's say, so this nozzle will work only with small inlet pressures, or it, in other words, it will generate very low gas density profiles. So we will not put pressures like we put with conical nozzles, you know, like 20 bar, 30 bar, and so on. So here the pressure is very, very small, usually a few bars. And let's put 2 bars. So that means 200,000. And again, the initial pressure is slightly smaller than the gauge pressure. It doesn't really matter as time as it's smaller than this one. Hydraulic diameter, and here, if you don't know this, how to define it, help again. Help is your best friend. Help, apply, close. Now, if you want to see the inlet and to make sure that it's chosen properly, right click here and display. And here you can see the inlet. It's good to check this one just to make sure that everything is defined properly. For instance, outlet, again, right click, display. And it's not shown because it's very far away. But let's say display wall. And this is the wall. Now you can move this, the geometry, if it's not in the proper place, click on this and you can move it. So this is the wall, and now if I click on outlet, this is the outlet. All right, now let's define the pressure at the outlet. Don't put 0. You might be tempted to put 0 pressure. Don't do that. Put a real pressure, which is usually a few millibar or 0.001 pascals. Pascal is by default the unit. I keep it like this because it's better. Hydraulic diameter again, and here doesn't really matter what you put, as time as is a decent value. Close. All right, and we finished here. The rest of the things we don't use now, so we don't have to change anything. Methods, make sure that we have second order upwind. So this is a very accurate numerical method. So the rest of the things we will not change by default. If you change something here and you can't remember what you change and how to change, just press default and it will put the default values. So these are the default values. Controls, again, we will not change anything here, but there will be a few, sometimes is required to reduce the current number. If the simulation will diverge, this is one of the things that you can try. I don't like this one. I have better solutions, but if you don't really have an option, you need to reduce the current number to 1, 0.1, 0.01 for instance. But the drawback is that the simulation will take much longer as the current number decreases. So the current number is the, if you want to name it, the speed of the simulation. So each step takes a certain amount of time. The smaller current number, the longer that time will take. Check again, what does it mean? The current number is related to the mesh and the flow. So if you have a very fast flow, supersonic, hypersonic, the current number has to be smaller and smaller. Or another option is to decrease the cell size, but again the simulation will take much longer because obviously you have many more cells in your simulation. All right, now report definitions we don't use at this point. Monitors, okay, residual by default is 10 to minus 3. I like 10 to minus 5, even if you don't reach it necessarily. You might reach it or not, but I prefer 10 to minus 5. It's not the most important criterion to reach convergence, so don't worry about this one. Okay, and now report plots. I like to monitor the flow at the outlet. When the flow doesn't change anymore, or more specifically the density of the gas doesn't change anymore at the outlet, that means it's another criterion to reach convergence. So just press new, here new, surface report, and whatever you want to choose. I choose maximum and maximum of density and the outlet. Okay, and this one we need to add it. So whatever you add here, it will be plotted on the screen. Okay, and yeah, for some reason so delete, it doubled, so you will have two plots. You don't need, you just need only one of these. Close. So we have the report plots. Okay, and the next step will be to initialize. So initialization will calculate rough values for the it will give rough solutions, and that will be the starting point for the simulation. So it will use a very simplified model to give the initial solutions, and also be refined as the simulation is advancing. So just press initialize. And normally this value should be greater than 10 to minus 6. If it's not, then you will have here a warning. You don't have to worry about that one. The simulation might be okay. I mean, it might run properly. So this is by any means, it doesn't mean that if you have here 10 to minus 9 or 10 to minus 12, the simulation will run without any problems. So, but it's good to have a very small value here. All right. If you don't have a small value, that tells you that you need to decrease the mesh size or increase the number of cells in your mesh. That's a warning that is related to the mesh size. Okay, so calculation activities. If you click on this, now it's a good idea to autosave. If you leave the simulation run unsupervised, you might not observe if it's going wrong, so you might you might have to start it from the beginning. So if you save it periodically, you can always go back, so with file and import data, and whatever was saved, you can go back to 500 iterations, 1000 iterations, and so on, to rerun the simulation and to change some settings and rerun the simulation without starting from scratch. So you can put here how many iterations you want to save, so every 1000, every 500, whatever. So let's say every 1000, and from here you can keep all of this, so to save every 1000 and keep all the auto saved, or just a certain number. I use this one, so every, let's say 5, depending on how much storing space you have. If you have a lot of storage, then you don't have to worry about this one. You can keep it like this. Okay. And here you have execute commands. So the nice thing about Ansys Fluent, and many programs, is not only Ansys Fluent, but this option here is that you can run batch simulations. So you can define here what to change in your simulation and run it automatically. So you have here automatically initialize and modify case. So if you want multiple pressures, you can define it here with create edit. We will not use it now, but you just have to learn how to do it. You can change the pressures, you can change the gases, you can change all sorts of simulation parameters and save it automatically. Run calculation now and check case in case you forgot something or you did something wrong. You will get a warning here. So check case, no recommendations. So most probably you haven't done any mistake. Number of iterations. So for the simulation, it's good to put a big number, but it's not a problem if you put a small number and the simulation stops when it reaches those number of iterations. You can always carry on. You can always stop the simulation at any point. You don't have to worry about losing losing the result. So you can put here 1 million or something. So each time you stop, it will start the counting from 0. So if you run 500,000 and you stop it, again it will run from up to 1 million or whatever number you have there. Don't worry about this, just put there any number. And now before running the simulation, I like to prepare to take some lineouts above the outlet, just to check from time to time the profile. This is not the proper place to analyze your simulation. So this is just to check, to analyze the simulation. You will use here. So from results. So this, if you double click on results, it will open what is called CFD post, and there you analyze your simulation, extract the data, organize, and so on. This part is used just to run the simulation and check if the results are what you expect. So in this point, let's take so double click on plots, XY plot, and density, and let's define some let's take some lineouts above the nozzle. If you remember earlier, I mentioned that we need to know how big is the domain, and here is very, very important. So the direction is of the flow is in X. So we have the outlet is a 200 and is going up to 205. So if you take 201, that means we have 1 millimeter above the outlet. And we will take it exactly, so you see here the flow, so this is the direction, so from Y is from here to here, and Z is in this direction, or Z, whatever you want, whatever is how you want to pronounce it. So Y is from minus 15 to 15, and let's call it this one X1, so it's 1 millimeter above the nozzle. Create. Now if you have some weird settings here, I mean weird numbers, and you don't cover the domain, you will have here a warning. Now 2 millimeters above the nozzle, alrighty, X2, create, and let's take another X3, 3 and 3, create, and that's it. Close. And now, so let's choose all 3 lineouts and let's plot them just for the sake of plotting. So it looks like this because it's not activated the other dimension, so plot. So you see now, even with these rough values that the initial values that I told you about, this is a profile. So as I expected, it looks quite flat top, but don't get fooled about this. Just because this point is flat, it doesn't mean that when the simulation is done, it's still flat. So you might have surprises. But I always check this one to make sure that I get the density profile, any kind of density profile. So that told me that the rest of the settings are okay. Now here, if I choose 0, so that is just around the outlet, having as a reference the 0 coordinates. So these are the profiles. From my experience, it will be a flat top profile, so I don't expect any surprises. Close, and now you can run the calculation. Even if so when you start the simulation, it will save automatically, but it's good to have this habit of saving periodically. So just save project, just to avoid any weird surprises. All right. So everything is okay. It's saved. Done. All right. That's it. And now let's start to calculate. So we have here the residuals. This is the former window. It didn't disappear whatever you plotted, so don't worry about this one. This is important. So the residuals, you will gain experience, so you will know what type of simulation will work properly, and when you have to watch it. So the most critical point, the most critical iterations are at the beginning. So first 100 or hundreds of iterations. So if you will have a problem with the simulation, that is the moment when you will have it. So if you see any problem, you stop the simulation and you start to adjust parameters so that the simulation will run properly. And here is the density. The outlet is going up, down, whatever, depending on the simulation. So let's wait for a bit and see how is it going. So you see each curve represents, so for instance, continuity, velocity. So the numerical method solves the equation for each one of these. Now you see here, it suddenly went up. So it's the solution, the simulation tended to diverge, but the Fluent can detect this kind of behavior and adjusts the simulation of the flow. So the time step, what is called the time step, reduces the time step so that the divergence is avoided. It sometimes works, sometimes it doesn't. So when it doesn't, you need to intervene and change the parameters of the simulation so that you can get convergence. So yeah, for now I will stop the simulation just to show you the next steps. So let's say everything is fine, the simulation converges. So converges means this one is going down, so the residuals are going down and they don't change anymore, or they reach 10 to minus 5, or you just satisfied with the residuals. So let's say you like you want to stop it at 10 to minus 3, or they reach 10 to minus 3 but they don't change anymore. So that means the simulation is one of the criterion for convergence. The next criterion is this, the density at the outlet doesn't change anymore, or pressure at the outlet doesn't change anymore. So pressure is or density is they mean the same thing. So when this one reaches a point where it doesn't change anymore, so it will be a flat plot. And last but not least, so this is the most important criterion for convergence. If you go to reports, double click on reports, check fluxes, setup, and mass flow rate. And when you check this, the difference between this, the mass flow rate at the inlet and outlet, has to be as small as possible. So ideally less than 1%. In this case, as you can see, the difference is huge. So you need to run the simulation until these two values are very close and the difference is less than 1%. And when you have all these three criteria, so the residuals, the solution doesn't change, and the mass flow rate is very, the difference between mass flow at inlet and outlet is very, very small, the simulation is pretty much done. So in that case, you check if it looks all right, plot. So the profile is still flat top. It's the beginning of the simulation, so it didn't change much. At this point, if this is the only thing you are interested in, so the density profile, which I'm interested, I pretty much I don't care about anything else. This is what I need in my experiments or when I design a nozzle. The density profile, I don't care about anything else. So what you can do, write to file, you check this, order points, and write, and you can save. So if you give it any name here, this will write an ASCII file which contains, so let's say, yeah, I will give it an example just to see inside, so to see how it's looking like. So if I go to what I saved is this one. So if you right click with this one and open with Notepad, for instance, Since it's ASCII file, you will not have any problems to open it. And now here you have to be careful, because here on the left side is the length dimension in meters, and here is the density in kilograms per cubic meter. So you need to transform this to get in other units like atoms per cubic centimeter. So be careful about this one. So here you will see is at x1. So this is 1 millimeter above the nozzle. This is the profile. And if you go down, here is x2 and so on. So depending on how many line outs you have, you'll export all of them. Yeah, I mean, to properly analyze the data, you have to go, like I've told you, with CFD pose. So this one, you can also plot how they are called, contours. You can plot it also here, but that program used to analyze the data is much more sophisticated than than the options that you have here. Yeah, you can do here, for instance, if you have here an if you have a surface defined, you can plot it. Now you can also plot, if you choose so, the interior of so the entire profile, the 3D profile of the nozzle, but it's not a good idea because it will take a very, very long time to load the data. So yeah, the simulation is pretty much done. Again, you can stop it, save it, and so now it will save the simulation at this point. Okay, and now let's say you run the simulation, but you did something wrong, or you want to go back to change some settings. You can go to import data, and you can, so you see here it's iteration 1, 2, 3. You can double click on this one and you can go back, or you can go back to initial one. So here we will see also the auto saved data, so you can go back at any point and modify it in any way you want. Okay, so yeah, we stop it, but we can carry on. If we go this one, you see it, the simulation is running. So yeah, I will stop here, and I don't know what will be the next tutorial. If you have any requests, let me know. If you want to support future video releases, you can do it. Check the video description. Thank you.